Hello, we should continue now about talking about pulse lasers. So far what we have explored is continuous wave operation of a laser, basically an ytterbium doped fiber laser, and we, as I said, we explored continuous wave operation, which in time would look like this, on which P out is a constant line at a certain power level with a certain characteristic of relative intensity noise. And we also mentioned how by opening the cavity, the laser cavity composed by the fiber, and then closing it down, we could make it tunable by exploring the whole emission spectrum of ytterbium. We can make a tunable laser source, fiber laser source in fact. But in this session we will explore what happens, or how we would be able to design a Q-switch fiber laser, which is in this case, which means a pulsed laser, a pulse operation laser. So first of all, let's define a Q. The Q of a laser is the quality of the cavity. Quality defined by the gain divided by the losses. And at the same time, the Q of a cavity implies or is related to the capacity of the cavity to store energy. So when you store energy, the next procedure or the next step is to release the energy. And the releasing of the energy would become be expressed in terms of pulses. So when we talk about energy, the energy for any photon would be the multiplication of Planck's constant times the frequency of such a laser. Please bear in mind that we don't talk about frequency in optics, but mainly in optics, but we talk about frequency, where lambda equals c divided by frequency, in this case nu, or in that case f. Okay, so this is wavelength, the speed of light in vacuum, and the frequency, or in that case the nu. Okay, so the basic structure of a Q-switch fiber laser is roughly the same as the continuous wave and the continuous wave tunable fiber laser. It has a pump source, a collimating lens, which collects all the light beam or the energy beams from the pump, focusing lens, which focuses all the energy into the doped core of the fiber, and a dichroic mirror. The characteristic of the dichroic mirror is that it has high reflection at 1064 nanometer, which is the main wavelength of operation of ytterbium, and high transmission at 976. Well, I made a mistake here. We chose on this occasion to work on 915 nanometers because it also represents a spectrum of absorption. I mean, a wavelength choice of absorption in the spectrum of ytterbium. So let's say that we work with 915 at this time. 915 is a wavelength of operation of the pump laser. So the same as in the previous schematics, we start pumping. There is absorption of the ytterbium ions. We reach threshold. Threshold means that the gain becomes equal to the cavity losses, but please bear in mind that the cavity was open in this occasion. I mean, this is open as in this case. So what we have here is a switching device. In this case, an acousto-optic modulator. An acousto-optic modulator is nothing else than a Pockels cell, on which you can increase or decrease the refractive index of the material inside, or by means of a radio frequency signal. So a radio frequency signal, which is a sinusoidal, it has a sinusoidal behavior. opens or closes this device. So this is it's like a gate, like as if it was a mechanical gate, but it's an optical gate. So it opens and closes the device, the reflection of the device. So there, at some point when it's closed, obviously there is no cavity and there would not be any energy out of the laser. But if according to the the radio frequency signal, the acoustic modulator is open, then we will see what happens. So all the energy that is stored from the pump, from the absorption, and from the population inversion within the fiber waveguide is released in the form of a giant pulse. So let's look at three basic critical points. Let's look at this, for instance. So please consider that the pump is already there. There is absorption, there is population inversion, but there is no cavity because the acoustic modulator is closed. If the acoustic modulator is closed, then the cavity is open. So the energy out of the laser is zero. But let's think about this. When the acoustic modulator from the radio frequency signal is open, then the first photon that is here from the population inversion can travel along air, then across the acoustic modulator, is reflected back from the broadband source, travels again, and then travels all along the fiber. The fiber has certain length, let's say a few meters, let's say it can even be a few hundreds of meters, it can be kilometers, and it can be 1 or 2 centimeters, depending on the concentration that we use on the fiber. So let's say that it travels from there, across, all along the fiber, and then is reflected, it travels across the focusing lens, and then it's reflected from the dichroic mirror and goes to the output. So this would represent this first few milliseconds or femtoseconds or attoseconds of the pulse. If we go to this point on the fiber, on any photon that is emitted, it would represent more points on this curve, yeah, all along here, yeah, naturally. So let's talk about the middle of the exact middle point of the fiber. Then this would travel across the fiber, air, acoustic modulator, air, acoustic modulator, fiber, and then it would come out around here. So the middle point of the fiber would represent the real peak of energy of the pulse. Then let's think about any other point, so a bit far from the acoustic modulator, but at the beginning or in the near end of the pump. So the photon would travel once along the fiber, then acoustic modulator, reflected back from the broadband mirror, then again at the acoustic modulator, then again along the fiber, which means that these photons propagated 2 times along the fiber, then air, and then this. So this photon would represent in time this part of the pulse. So any other points around here in the fiber would be represented by these points in the pulse. Yeah. So there are some equations to calculate pulse duration. Yeah, pulse duration would be in time delta t, the pulse duration in time of the pulse, peak power. Yeah, energy of the peak as well can be calculated. And round trip. Round trip would be how long would it take for one photon to go from the near end of the pump to the whole trip in the fiber. Yeah. So this is another parameter that needs to be calculated. Round trip. So This phenomena would repeat again. I will try to write it a bit more clearly here. So it's the same time axis, yeah, P out or P laser. So what we would have is zero energy when the acoustic modulator is closed, but then as soon as it opens up, then we will have a giant pulse, and then relaxation because it will close again, and then absorption happens, population inversion happens, and a lot of energy is stored in the fiber cavity. Then we open again the modulator, another giant pulse, and another repetition of the period. So this would have also another parameter to be calculated for a pulse laser that is called repetition rate, which is directly proportional to the velocity or the speed of the switching on the focal cells, but also on the round trip of the fiber. Thank you.